Recording in progress.
Okay. So, hello and welcome to all to the second part of this talk on Lie categories. My name is John. I would like to again thank you for inviting me to this seminar, and I suggest we begin with this talk. So first of all, let's briefly repeat what was done the previous time. So we defined a Lie category to be a small category whose sets of objects and morphisms are smooth manifolds. So a category to be small merely means that the objects and morphisms are constitute sets, not classes, right? In addition to the requirement of the sets of objects and morphisms to be smooth manifolds, we also require the source and target maps to be smooth submersions, and there's this second natural requirement that the composition map and the unit map are smooth. So maybe just briefly, why are we requiring the source and target maps to be submersions? It's, for example, for this set here to possess a canonical smooth structure inherited by the product C times C. And moreover, so we always require the manifold of objects to have no boundary, but always, we permit the manifold of arrows, so of morphisms to possess a boundary. And in this case, we also require restrictions of source and target map to the boundary to be submersions as well. So maybe I should, Sasha, is it clear what source and target maps are? So just spits out the domain and codomain, right? All right, and so among the questions that we pondered about was whether the set of all invertible elements, so the set of all invertible arrows G of C, which is also called the core of the category, whether this is whether this has a smooth structure, and in order to get to sufficient conditions for this, so for the core to indeed possess a structure of a smooth manifold, we found that we had to impose additional conditions. One of these two, either the units of the category needs to be strictly contained within the interior of the category, or on the other hand, they are fully contained within the boundary, and moreover, the boundary itself is a subcategory of the category. And in this, so if one of these two conditions hold, then the core is indeed a Lie groupoid, so it inherits the structure of a smooth manifold, and everything plays out nicely. And so in the first case, it's going to be open in the interior, hence in the category, so in the space of morphisms itself. And in the second case, it's going to be open in the boundary of the space. The core is just the set of all invertible arrows of the category. So this something like this, right? So maybe I have to define what invertible means also. Just means there is a unique morphism such that the product G, G-1, and G-1G is the appropriate unit. All right, so then we briefly discussed the infinitesimal structure of a Lie category. So this would be a certain kind of equivalent of a Lie algebra to a Lie group. And so because now we have many objects and not just one, right? As in the case of a Lie group, we call this Lie algebroids. And so how are they defined? Given a certain Lie category. So for example, let's just take a look at the left one, or the so-called left Lie algebroid. So this is a vector bundle over the space of objects of our Lie category. Well, it's a vector bundle. What are its fibers? The fibers are defined just by the kernel of the differential of the tangent, the target map, when we take a look at its value at 1x, right? And so what even is a Lie algebroid? Well, it's basically a kind of a vector bundle with additional structure that allows you to kind of take the Lie bracket of the sections of this vector bundle. This is like obviously for tangent bundles, this is always there, but for arbitrary vector bundles, it's not. So we have to impose like these structures additionally. And in the case of a Lie category, this happens naturally. So on the space of sections of ALC, how do we introduce the Lie bracket? Well, it's kind of similar again to the construction of a Lie algebra of a Lie group. So this guy, so the space of sections of ALC is going to be isomorphic to the left invariant vector fields on the category. And of course, these are sections of TC, and there we have the canonical Lie bracket, right? So basically we kind of transfer the bracket from TC to ALC. So the last piece of data that's missing is the anchor map, which is a certain morphism of vector bundles. It's a morphism from the algebroid in question to the tangent bundle of our object manifold. And so, of course, we already used one structure map, right? And we this is the only choice that's kind of left. So we use the differential of the source map in this particular case. So, and what's not written on this slide is that like these two guys are kind of compatible in a way. We have a certain kind of Leibniz rule, which would read something like this. So, this is F. Right. So yeah, basically it's the Leibniz rule when this row is just the identity, right? But of course, since the sections of an arbitrary algebroid don't give a the sections of an arbitrary vector bundle don't give a means of directly differentiating functions, as is the case for the tangent bundle, we need to use the anchor map. So this is kind of the compatibility of the two. Okay. And for the purpose of today's talk, I also want to introduce this piece of notation that we've already encountered. So for any morphism of our category, we denote the precomposition and postcomposition by LG and RG. This is supposed to kind of remind you that on Lie groups, this is nothing less than the left multiplication and right multiplication. And So there is a piece of notation here that's kind of also missing. So C and index above X is just the target fiber at X. Of course, X is here an object of our category, and well, of course, index below is going to mean the source fiber at X. And of course, well, if we take a look at a certain arrow of our category, right, we can only precompose this arrow with certain arrows that have target equal to source of this arrow, right? Because otherwise there's like really no hope of kind of composing the two. And so what precomposition spits out is the product GH, and the target of this guy is precisely the target of G, right? So this is kind of a piece of notation that we are going to be using. And yeah, in the point is kind of that in any Lie category, these maps are automatically smooth. So we can consider, let's say, their differentials or ranks or anything of the sort, right? And that's precisely what we are going to do. So the first thing that we are going to kind of consider in today's talk is the rank of the differential of this left or right multiplication, or if you want to call it pre or post composition map. So we are going to denote by rank LC of G the rank of the linear map that is the differential of left multiplication by G at the appropriate unit. Okay, we could use any other kind of morphism that's composable by G from the left, but of course there's a distinguished one, and we use that one. Okay, and so some more nomenclature is that a morphism has full left rank if the left rank equals to the codimension of X in C. So why is this considered full? Is, well, for the simple fact that if you have left multiplication, it just goes between target fibers, right? It's a map between target fibers, as already said, and this is going to be a submanifold of codimension X in C, right? And the same holds for this one. So that's kind of the maximal rank of this map, if you will. So yeah, we're going to say that a morphism has full rank if this holds, and we're also going to say that it has constant left rank if the precomposition map by G has constant rank. And the first example that's kind of trivial in a certain way is the rank of an invertible morphism, right? So an invertible morphism, an invertible morphism has an inverse, right? So what I want to say is the left multiplication by an invertible morphism has an inverse, and its inverse is precisely the left multiplication by the inverse, right? This is just the same thing as in the Lie groups that we're all used to. So, and because this is because LG is a diffeomorphism, this is obviously going to hold that the left rank is going to be full and constant, and the same holds for right rank. Okay, so and the first thing that we want to kind of focus on is, of course, the example that is kind of that is the example of the Lie-monoid of matrices for multiplication, for matrix multiplication. Well, since this is a vector space, we can identify its tangent space and the identity with the vector space itself. We can identify the left multiplication by a matrix with its differential because this is a linear map, right? And so we basically need to, so in order to ascertain what the left rank of any matrix would be, what we have to do is we have to compute basically the image of this guy and take a look at its dimension, right? So in order to do so, we work with a canonical basis, Eij, and it turns out we get these kinds of expressions, and so these two guys are obviously going to coincide because of the properties of matrices, that the rank of the transpose matrix is just the same as the rank of the matrix, right? And so what we get is that the left rank of a matrix, like as seen through this new notion, is the product of, so the dimension of the underlying vector space times the usual rank of the matrix, right? So in a certain way, this notion of a rank of a morphism now generalizes the usual one from linear algebra. And yeah, in this case, obviously, the left and right ranks are going to coincide. So, and the very next example that I kind of want to show, but is again kind of linear and one object, is the example of upper triangular matrices. So if you consider 2 times 2 upper triangular matrices, you can, in the very same way that we just did, we can compute the so images of right translation by these 3 elements, or the left ones. And so this is kind of really easy, right? Because the only thing that you need to do is compute all of the possible products of these 3 guys, and what you get is so basically the answer to the question whether in any Lie monoid the left and right ranks coincide. They don't, right? Okay, so these are kind of 2 examples, 2 easy examples of ranks. And so now I would like to focus on the general properties of ranks in any Lie category. So not in Lie monoids, not in any kind of Lie monoids or Lie categories with additional linear structure. So like to can you guys over Zoom see this part of the board?
Yes.
Yes.
So the general properties would be the following. So first of all, this guy is kind of easy, right? Because well, the left multiplication by the product of 2 composable arrows is nothing less than the composition of the left translations of the respective left translations, right? And of course, yeah, what you need to use in the end is the fact from linear algebra that this is less or equal to these guys. So this first property is really simple. The second property, so for the second property, the upper bound was kind of already cleared up, right? But not the lower bound. So how do we show the lower bound? Well, the only thing that we need to kind of observe is that we have a certain commutative triangle. So this is left multiplication by G. Now we have source maps going into the object manifold, and basically differentiating this commutative triangle at the appropriate unit gives us the lower bound So the rank of the anchor of the left algebroid at so at S of G should be less or equal to the rank, the left rank of the morphism G. Okay, so the next one is kind of well, it's reminiscent of the fact from linear algebra that the set of all invertible matrices are open, right? It says that the set of all full ranked arrows is open in the morphism space. So how do we show this one? Well, the main trick is to kind of see this particular map. So any morphism G would be mapped to the differential of the left translation by G, and you could see this as a map that goes from C. So maybe I should, in order to clear this stuff up, I should say what this map is. Well, this is nothing other than a linear map between so these two vector spaces. And so how do we see this map? Well, we see it as the map from C into so I'm going to write it like this, as star U star kernel of dt, and take the dual and now tensor it with kernel of dt. Okay, so basically this guy can be seen as a section of a certain vector bundle, right? And inside this vector bundle, we have basically the set of invertible matrices, and now take the pre-image of this open set with respect to a continuous map. So that's basically that. And the last among the first simple properties is lower semi-continuity, which basically says that for any morphism in our category, there is a neighborhood such that on this neighborhood, the left rank is at least that of the morphism that we started with. And this is proved in basically using this map here. I don't want to go into too many details regarding this. So are there any questions so far regarding this?
Yes, a quick one. So if G is invertible, then it has maximal rank.
Yeah.
So can you give us some example of an element which is not invertible but still has maximal rank in some?
We are going to encounter them, a lot of them, basically. For example, any Lie category that is extendable to a Lie groupoid will be of such kind. So we'll have maximal rank. So a very simple example would be the monoid that is the closed semi-ray from 0 to infinity for addition, for example, because it's it's extendable to the Lie group R plus for addition, right? And we're going to see that any such Lie category has all morphisms full and constant rank.
Okay, thank you.
If you don't have zero divisors.
Basically any kind of absorbing element such as a zero would automatically have zero rank, right? Because
So what I'm saying the opposite. If you have, something which is like a ring without zero divisors, then essentially you can extend it.
Well, Yeah, there is a certain kind of construction. I think it's called something like growth in the group or something like that. But it works only for a billion monoids, I think. There's also a more general construction. Yeah. All right, so let's continue with these properties of ranks. So kind of the first of these two that's well, the one that's on the board right now is saying that basically like it doesn't matter at which invertible element you measure the rank of a morphism. Okay, so we just choose the identity because it's the distinguished element, right? So, and this is kind of in accord with the mentality that has been kind of put forward the previous time, that the units dictate what happens with invertibles in a Lie category. So, and how do we prove this one? Well, we prove it in the following way. This is a little bit trickier, maybe. So what we do is, okay, first of all, for the sake of simplicity, I want to work with no boundaries at this particular moment. So our Lie category has no boundary, okay? And what we do is we consider the action of the core on the category itself, okay? And this is going to be a category on its own. So, so this is nothing else but the fibered product, okay? This is kind of the set of all pairs GC, such that the source of G is the target of C, okay? And so what are the structure maps inside this category? Well, they're kind of obvious when you think about it. Like the source of a pair just spits you out the member of your category. The target just multiplies these two guys. The unit is going to so the unit at C is going to be one target of C, and not only do we have these three maps, we also have that this guy is a groupoid. So and I should also say what's the multiplication. So we can only multiply pairs that have kind of these two guys coinciding, right? So, and this would be pairs of the following type, right? This guy here should be the composition of G and C. And what do we do? Well, we just multiply H and G and leave C as is. So yeah, this now gives the structure of a category. And moreover, it's a groupoid because GC can be inverted. So this is kind of easy to show that this is its inverse. So, and not only is it a groupoid, but because of the smooth structure on G of C and C, this is also a Lie groupoid. So basically it has a smooth structure. And this is kind of the thing that we need to use in order to prove this thing. So how do we do that? Well, Lie groupoids have this kind of quality that the target map restricted to the source fibers has constant rank. Okay, so basically target map restricted to source fiber has constant rank. Now, if you take a look at these expressions, what you get here is that, so this is precisely right multiplication by C restricted to the core. Well, of course, you have to keep in mind what you can multiply this with, and this is just going to be the source of the invertible element has to be the target of C, right? So this is our notation again. So, and this guy has constant rank now, and that's basically saying, right rank has this quality that's written on the board. Okay, and for the last one, so you can see we're kind of ascending in difficulty here. How to show certain properties of ranks. The last one would be that the images of differentials of left multiplications form a certain distribution on our category. Okay, and so this distribution is singular in the sense that that the fibers of this distribution have varying dimension. Okay. And now, so it's also this particular guy is integrable. So that just means that basically there's a decomposition of our category into maximally connected, weakly embedded submanifolds. And these turn out like to be precisely like the integral manifold of this distribution D is nothing but the left multiplication by the element through which our integral manifold is going of the core, basically, of our Lie category. So, and you can see that its dimension is varying because the dimension of the integral manifold is precisely the left rank of this particular element in which we are taking the integral manifold. Okay, so this is kind of as far as the properties of ranks go. So now, as promised, I would like to also talk about extensions of Lie categories to Lie groupoids, which are going to have the property that Ture has inquired about. So we've seen examples of Lie categories arising from Lie groupoids by kind of just throwing a bunch of the arrows away from from our Lie groupoid, but kind of leaving all of the objects there. What are kind of the examples of this? Well, the first one is the closed ray from 0 to infinity for addition, right? This has already been talked about. Well, what about any multi-object examples? Well, one multi-object example would be the order category. So first of all, take R and form the pair groupoid. So this would be kind of S of y x is just x, target of y x is y. How do we multiply? Well, multiply like this, and the units are also given by unit of x is just x, and also this guy is a groupoid because you can kind of switch the rows of x and y. So yeah, this has a kind of a picture, right? It's just the two-dimensional plane, right? And now we can throw half of the arrows away and yield just kind of the half space, the closed half space below the diagonal, so that our category is literally going to be so the pairs y comma x, such that y is greater or equal to x. So this is what's meant to be the order category. Okay. And so such examples of Lie categories that arise in this way should kind of be understood better, because they're the examples that you usually kind of have in mind when dealing with Lie categories. So, and we henceforth define what an extension is of a Lie category. It's just a Lie groupoid together with a smooth injective immersive functor over the identity. So on the object space, we just leave everything as is. And on the morphism space, we kind of injectively immerse the morphisms of a Lie category into our groupoid. So in other words, this just means that G is a Lie groupoid and C is its wide Lie subcategory. Wide means precisely it has the same objects. Okay. And more nomenclature. So such an extension is called weakly et al. If the dimensions of the extension and the category are the same. Okay, and these are going to be kind of nice extensions. Like this one can be obviously seen as a, like this is a weakly et al. Extension, right? Of the order category to the pair groupoid. So yeah, let us start discussing the properties of such Lie categories that admit extensions to groupoids. So the first thing is kind of independent of any smooth structures. So it's regarding the cancellativity of morphisms. So basically, cancellativity would mean like left cancellativity of an element G would mean that that if this holds, then H is equal to K, and this can immediately be identified by left translation being injected, right? So if we have so an extension, right? What we do now is we basically just apply the map phi, and notice that I'm already using the functoriality of phi. And of course, pi is the extension in question, right? And now this particular product lies within the groupoid, so we can cancel these two out because we have inverses, right? And now just use injectivity of phi. So that's it. Notice no smooth structure was needed. Everything is basically some categorical algebra, if you will. For the second one, so this is the one that Jure has inquired about. All morphisms have full and constant rank. How do we prove this? Well, basically what we wanted to show is that this guy is an isomorphism whenever G and H are composable, of course, right? And so in order to show this, what we do is we use functoriality because that's kind of the only thing that we have. And so what we do is we have left multiplication by G. Okay. Now we also have phi restricted to the appropriate fiber. Right. So this is going to be the groupoid that's extending our category, and because of functoriality, it preserves the so the object over which the target fiber is taken. And here we're just going to have L phi of G, right? Okay. So this is the commutative diagram that's a consequence of functoriality. But now, because like there's some smoothness going on, we can basically take the differential of this diagram, right? So to be a bit more precise, what I will do is I'm going to say let this be 0. So I'm taking a look at the kernel of left multiplication by g. Well, it's differential, and now apply phi, or the differential of phi, d phi at gh, d lg h of v. This is equal to 0 still, of course. And now use basically the chain rule. So what we get right here is that differential of left multiplication in our group by phi of g at phi of h times d phi h of v is 0, right? And now just start using the fact that that we have a group point and that we have an immersion, right? So because this expression now lies within the tangent space of the group point, so this guy is an isomorphism. So this is going to imply that this guy is 0, right? So d phi h of v is 0. And now, because pi is an immersion, b is 0. So you can see that this is the proof that the kernel of this linear map is trivial, and hence this is an isomorphism. Okay. And for the last one, so if we have the very nice setting of a weakly et al. Extension, then the left algebroid of our category is going to be isomorphic to the algebroids of the groupoid. Well, of course, there's a canonical identification, as has been mentioned in the previous talk, between left and right algebroid in any groupoid, because we have inversion. But in a general Lie category, there is no such thing as inversion, right? So we have to bear in mind the fact that left and right algebroids may be non-isomorphic, but that's not the case with weakly et al. Extensions. And this is also basically just a consequence of functoriality. So how do we prove this guy? Well, what we do is we consider the following diagram. So we have target map of C and we have target map of G. And because of functoriality, this diagram commutes, right? So again, what we do is differentiate this diagram. So basically, this is this. Now take the kernel of differential at the appropriate unit. So 1x at any unit. Okay. And what we're going to get is kernel of dtc at 1x is equal to the kernel of the composition of two linear maps, right? And this is, well, what's this? This is nothing but d phi at 1x pre-image kernel dt g at 1x, right? So this is the question of what's the kernel of a composition of two linear maps. It's just the pre-image of the first map, and yeah, take the pre-image of the kernel along the second, along the first map. So, and okay, now apply d phi again what we get is d phi 1x of kernel of bt 1xc. This is under kernel btg at 1x, right? But now because so phi is an immersion, and these two guys have the same dimension because of the assumption of weakly etalness. This is actually going to be an equality. So basically, this equality ensures that we obtain a morphism of algebraics. So it's going to be a Python-wise isomorphism, hence it's going to be an isomorphism of vector bundles, and because of functoriality, it's going to be an isomorphism of algebraics. Any questions? Okay, if not, let's continue to maybe a bit less, a computational, a bit less computational part. So, why are extensions nice? Well, first of all, they enable us to positively answer the question that we had in our previous talk. So, are Lie monoids parallelizable? We know Lie groups are, right? And the question is whether the same holds for Lie monoids. And in the case where a Lie monoid is extendable to a Lie group, this is indeed true that the parallelizability holds. So, and why is this the case? Well, it's just well, I'm a loss for words here. Your differentials are isomorphisms, and your trivialization was given by essentially just extending basis at the of the Lie algebra of the Lie group, extending it with left translations, right, to the whole, to a kind of a global frame of your tangent bundle of the Lie group. Well, because we have this property that all left ranks are full or right ranks, this is going to hold in the case of Lie monoids as well, right? So this is kind of using the same trick as in the Lie groups case. And another property would be, so you have a Lie category, you consider the Hom set CXY. So these are just all of the morphisms from fixed X to fixed Y, which are objects, right? And you just pose the question, is this a smooth manifold? And in the case where a Lie category is extendable to a groupoid, this holds. If not, we don't know. So this is still an open question for the case of non-extendable Lie categories. And yeah, as a consequence, if you consider all of the morphisms from X to X, so over the same object, this is going to inherently have a structure of a Lie monoid, and this kind of result ensures that it's going to be a Lie monoid, right? So kind of a nice thing a nice quality to have in the Lie category. So if you guys have any idea of how to find Lie monoid that doesn't have a trivial tangent bundle, please let me know, because I would be really interested in such an example. But it seems that constructing such an example is somewhat involved. All right. And one more example that we kind of used as motivation the previous time is the example of statistical thermodynamics from physics. So basically you are given a finite set of microstates. And what are even microstates? Well, they are basically, so how do we make sense of this? You have a large box of certain particles, each of which can be in one of the finitely many microstates. So, and a configuration of this system is a point of the n simplex. This is just like the probability that upon random picking of a particle out of that box, it's going to be in the ith, microstate. And so how do we make a category out of this? Well, you just take all of the pairs such that the entropy of the final state is going to be bigger or equal to the entropy of the initial state.
Just one thing, I'm going to let you be the host because I don't know where is the recording going to end up. So let's say better than it is if it is this computer.
Okay.
Okay.
Good.
Sorry, I need to
no problem. So in this way we obtain categories. So this is kind of, it's a toy example from physics, if you will. Any pair Q comma P is just is kind of identified with an arrow from P into Q, right? So we are basically saying, a transition between two configurations is possible if and only if the entropy of the final state is greater or equal to the entropy of the initial one. And so obviously, like the question is this a Lie category? And first you immediately observe this guy has a boundary, right? And we didn't allow our object manifold to have a boundary. Well, this conundrum is kind of solved by just removing all of the boundary points. And this is rationalized by the fact that the entropy is not a smooth function at points from the boundary. It's a continuous function. It can be extended to a continuous function from the interior of this guy to the boundary by noting that x times logarithm of x as x goes to zero. So you can basically extend s to the whole n simplex, but on the other hand, if you take a look at, for example, its first derivative, what is it going to be? It's just 1 plus logarithm of x, right? And as x goes to 0, this is going to minus infinity. So basically, the second computation here is saying that it's not going to be extendable to a smooth function on the whole n simplex. And so that's kind of the rationalization why it doesn't even make sense to kind of talk about the smoothness at that point, at those points from the boundary. And another problem which prevents us from saying, D is a smooth manifold, is that S has an extremum at P mu, as I denoted it. So what is P mu? Well, it's defined as Pi's are all equal. So this would kind of correspond to the configuration that has all of these probabilities the same. So this is, in physics, this is called microcanonical configuration. And yes, so what I'm trying to say right now is that not only do we have to throw away the boundary of the n simplex to obtain a Lie category, we also have to throw away this particular point. And how is this physically rationalized? Is by the fact that in a certain way, this configuration corresponds to equilibrium configuration at infinite temperature. So this is a kind of a physical physics thing, yeah. So, but taking the object space indeed to be just the interior of the n-simplex and without this problematic point, and taking the restriction of D to like only these objects, this is going to indeed give a Lie category. This is something that we proved in our paper. And so in physics, this, for example, provides the means for isolating the equilibrium configuration if we are given certain initial, additional data, such as the energy of I microstate for each I and the temperature at which the system is held. So this is kind of, I would say, useful in physics, or you can at least see it as a kind of a mathematical interpretation of what has been done in physics. And because this guy is obviously extendable to a Lie groupoid that is the pair groupoid over the manifold X, the algebroids are going to be isomorphic to the tangent bundle of X. Well, so here I am using the kind of maybe implicit knowledge that the algebroids of the pair groupoid are going to be isomorphic to Tx, so the tangent bundle of the object space. And moreover, all of the morphisms are going to have full and constant rank. So this is a kind of a nice scenario. These are kind of nice qualities to have. All right. Now, given that I still have 10 minutes or so, maybe even more. I'm not sure, when does this seminar end? It's Washington. Okay, so I still have enough time left. So we still have time to debate these certain qualities of left invariant and right invariant vector fields on any Lie category. So what's the motivation here? Well, on any Lie group, we know that left invariant or right invariant vector fields are going to be complete, right? And what does it mean to be left invariant or right invariant is just that such an equation holds for any G and H, right? But we can, of course, make sense of this in a category as well. So G and H must be composable. And additionally, oh, sorry, this is not right. Of course, the LGH of XH is equal to XGH. That makes more sense. So yeah, whenever G and H are composable, this can be made sense of. And moreover, well, in order to really say that this holds, you have to impose additionally that X is tangent to target fibers because of the fact that LG, again for the 100th time, is a map between target fibers, right? So this guy has to be a section of the kernel of DP. Otherwise, there's no hope that we can make sense out of this. Right, so this is the definition of what a left invariant vector field on a Lie category is. And yeah, so the question is, okay, let's start with Lie monoids. Are vector fields going to be complete? And of course, if you are given Lie monoid, for example, I don't know, unit disk, right? Unit disk, this is its identity right here, right? If you take an inward pointing vector here, there's really no point like, you're going to fall out if you go into like negative times, right? So there's really no hope that any Lie monoid with a boundary is going to possess this quality. But there is still hope that it's like that every invariant vector field is going to be half complete, in the sense that that any maximal interval on which the integral path of the vector field in question is defined is going to include one of the two closed half rays, right? So this is kind of our definition of half completeness here. And indeed, if we are given a Lie monoid that has a normal boundary, so I'm going to stop here and first kind of tell you what that means, like decipher what a normal boundary is, right? It's either E is in the interior of the monoid, or the boundary of the monoid is a submonoid. So one of these two things must hold. Like that's what this phrase means. So if we are given a Lie monoid with a normal boundary and let's say left invariant vector field, then we have the following two results. So this is kind of a generalization of the result for Lie groups. Now, if we have the unit lying in the interior of our monoid, or we have both that the second condition holds and that XE is tangent to partial M, then the vector field is going to, like, if it's left invariant, it's going to be tangent to the boundary at all boundary points, and it's going to be complete. So this is kind of the first scenario that generalizes, that also includes Lie groups. Okay, and for the second example, if we have that the unit, if we have the boundary is a submonoid, and we have that XE is either inward pointing or outward pointing, then we have half completeness. So then basically, what this is saying is that, first of all, the integral path of the left invariant vector field that starts at the unit must be the whole half ray, either the positive or the negative one, and moreover, X is going to be half complete. So what that means is that this positive half ray, for example, is going to be included in JGX for any G in the monoid. Okay, and the flow of the left invariant vector field is going to be given, just as in the case of Lie groups, by right translation at the appropriate point. Okay, so well, maybe I can give you a kind of an idea of why this holds, just so I don't state results without giving any kind of justification. So first of all, if we have that, so if we have an inward pointing vector, so say X G inward pointing, right? At G from the boundary of M, then there's really no hope that there's no hope that our JGX is going to contain an open interval around 0. At best, it's going to only contain a small interval around like a small half-closed interval. Okay, and on the other hand, if we have that, for example, XE is tangent to the boundary, well, because of the assumption of the normal boundary, we can translate it along the boundary, and it's going to be everywhere tangent to the boundary, right? Because the boundary itself is a submoment. So in this case, what we're going to get is that JEX contains an open interval around 0. So kind of we have these two like different cases, right? Well, the same holds when E is in the interior, right? Because now in that case our E is in the interior, so there's really no problem. We of course have the open interval around 0 again. And now, in order to really show this stuff, what the gist of the argument is that if this guy is the integral path of x starting at E, then the composition LG with this path is this guy is going to be an integral path of x starting at G. Okay, so basically, this observation is central to this theorem, and it's basically the same observation that's made for Lie groups when proving that they're complete. And so, using these two results, I'm not going to go into any more detail because I don't want to bore you or lose you any further. So basically, this is the gist of the argument. And I would say two interesting corollaries of this result are the following. So if you have a Lie monoid and you have the unit line within the interior, then the elements in the boundary cannot have full rank. Okay. So, for example, this is now a simple corollary of the previous results. If we have the unit lying in the interior and the boundary is non-empty, then our monoid is not going to be extendable to a Lie group. Okay. So, and how do we show, for example, this particular guy? Well, contradiction, right? By means of contradiction. So we assume there is an element G in partial M such that this is an isomorphism, right? And take an inward pointing vector. So at G of an inward pointing vector B at the boundary element G. And now, because this guy is an isomorphism, we can extend this vector to a global left invariant vector field on our monoid, and then this goes against what was said in the previous theorem, right? That our vector field must be tangent to the boundary at the boundary points. So this is like a very simple corollary now, and a similar result basically also holds for Lie categories as well. So if you have all of the units lying within the interior of your categories, then the morphisms in your boundary of the category cannot have full rank. So basically, again, you get the abstraction to being extendable to a Lie groupoid. All right, and so this is basically what I wanted to say in today's talk. There's a lot of possibilities for further research with regards to Lie categories. So, for example, the first one that's currently ongoing for me is the construction of an isomorphism between the left and right Lie algebroid when you have the boundary a wide subcategory. So then, of course, we have the mentioned open questions, whether Lie monoids are parallelizable, whether Hom sets are submanifolds. Then you have the question of existence of a class of algebroids that integrate to Lie categories, but not to Lie groupoids, right? This kind of question of when Lie algebroids are integrable to groupoids has already been solved by Rui Loja Fernandes and Marius Kreinig. But now, you know, this kind of theory opens up new questions regarding whether new classes of Lie algebroids that can be integrated to Lie categories exist. And then there's the kind of nasty question of infinite dimensionality. Of course, like if you try to generalize the case of statistical thermodynamics to when you have infinitely many countably infinite microstates, you're going to get a certain kind of infinite dimensional Lie category. And then, of course, another example would be the tensor bundle. This is kind of a bundle of Lie monoids, right? And it has infinite dimensional fibers. This is kind of opposed to the exterior bundle that we've discussed the previous time. And such a generalization to the infinite dimensional setting seems possible because basically transcendentality theorems for manifolds that are modeled on Banach spaces. So this theory has been developed in the 90s, and so basically all one has to do is just use that theory. It seems like a manageable mission. And then you have the question of multiplicative structures, so multiplicative symplectic forms or multiplicative Ehresmann connection on Lie categories. This kind of structures have been researched for Lie groupoids, and now, of course, like there's an analogous kind of notion for Lie categories, and the question is whether you obtain any new phenomena that you haven't obtained in the you know, in the like invertible context. And there are also hard systems, smooth sieves, smooth Grothendieck sites, Morita equivalences for Lie category. There's really a lot of kind of directions to pursue in this theory. So I'd like to thank you for your attention, and if there are any questions, I am all ears.
Yeah.
Yeah.
So do you have any examples of Lie algebroids which are integrable to Lie category but not to Lie groupoid?
Yeah, that's precisely what I asked here, right?
So do you have a single example? No example.
No, I don't have that example. No, like the only ones that I kind of obtained was in the end identifiable with a Lie algebroid that is the algebroid of a Lie groupoid. So So yeah, that's an open question. All of these questions are basically still open. But when I was talking to Rui Loja Fernandes, he said that that such a class of Lie algebroids could perhaps be obtained in the theory of complex Lie algebroids. So these are kind of like same as Lie algebroids, but you have complex, fibers over complex. Fibers are complex vector spaces, basically. Yeah. So that was his suggestion. Maybe look at that, but I haven't. Any other questions?
Maybe if I can ask something.
Uh-huh.
So how does this compare to the theory of local Lie groupoids?
So the theory of local Lie groupoids is basically you have two sets, just as in this you know, context of Lie categories, but your multiplication or your composition is only defined on a neighborhood of the units, and the same holds for inversion. You can only invert elements in the neighborhood of the units. So here, first of all, the composition is global, right? I mean, it's not really global, but it's defined on the whole category. And moreover, there's no assumption of of invertibility, right? So, and with regard to your questions, how these two kind of relate, so like this first item in this list that's shown right now, this ongoing research, is like basically constructing a local Lie groupoid around the boundary of the subcategory, and half of it is going to kind of coincide with the Lie category in question. So there's a connection between the two, and of course, in that case, you automatically yield an isomorphism between left and right Lie algebroids, because that's just the case for local Lie groupoids, right?
So in this case, if you have a Lie category without boundary, right?
Uh-huh.
Invertible elements are a neighborhood of the
Invertible.
So this
Yes.
is a special case of a local Lie groupoid.
Oh, well, not only is it a special case of a local Lie groupoid, it's just a Lie groupoid, right? You mean the whole category?
Yes.
Yeah, the whole category is basically going to be a local Lie groupoid. Yeah.
Yes, because I'm saying this because if this is a special case, I mean, the category of the theory of local Lie groupoid is quite well developed, right?
Yeah, yeah.
And there are some results about the extension of local Lie groupoids to global Lie groupoids, which is apparently completely solved. So it seems to me if these results if you would apply that results to Lie categories without boundary, this should be solved, I think.
Well, sure. So, but for Lie categories without boundary, this is not as interesting because Lie algebroids, like, first of all, the core is going to be open in the Lie category, right? So, like automatically the algebroids are going to be isomorphic, you know, and in this case, I don't think you get that interesting results. The interesting stuff begins to happen for Lie categories that kind of have certain intricate phenomena going on at the boundary, right? As was, for example, the case of the example of statistical thermodynamics that we've seen. For example, all of the invertible elements lied on the boundary of that guy, right? So it's kind of, yeah, I guess there are some intricacies with the boundary when it comes to Lie categories that you don't get with Lie groupoids. Any further questions? Okay, if not, let's conclude the Zoom session. Again, thank you for your attention. It's been a really pleasant thing to talk about Lie categories, especially at Faculty of Mathematics and Physics, where I was born and raised, essentially. Yeah, thanks again, and I guess I'll see you around at the topological seminar.